All right. Yeah. So cool. Let's talk about clicking and finding where you clicked. So here's an exaggerated view of a dot. And let's just put down the coordinates on the opposite corners. And let's remember this is actually x0 plus 50 and y0 plus 50, assuming it's a 50 by 50 box. How many people had Window Builder completely stop working? I have had Window Builder completely stop working, but it usually starts working again. If it's stopped for you completely, let's take a look at your code in office hours, because you might have something where you're asking it to do something that it doesn't know. Alright, so let's say that you click at a point xy. Okay, you want to find 4 distances, right? So distance to the left edge is x minus x0. Distance to the right edge is x1 minus x0, which is also x0 plus 50 minus x. Right? So x increases in that direction. So that's the larger value of x is x1, the smaller value is just x. And then to the top is y minus y0, and to the bottom is y1 minus y, which is y0 plus 50 minus y, because y increases going down. And so you can find these 2 distances. Let's call this left, right, top, and bottom. And then how do you decide which one is closest? Well, I mean, if left is less than right, and left is less than top, and left is less than bottom, then the person clicked on the left edge. And so use better variable names, but I didn't want to write out big long variable names here, but you know, distance to left, distance to right, and so on. So 4 of these if statements let you know which one did they click closest to. Now there will be ambiguity, right? If, for example, they click very close to a dot, they're going to be, you know, very close to the left edge, very close to the top. Depending on how you write your if statements, if they're exactly the same distance from 2 edges, right, it will pick one. Depending on how you do this. Now, if you do this with 4 if statements and each one is a strictly less than, it may not work if the distances to 2 edges are the same. Take that into account, right? So one way to do this is, you know, if this is true, they clicked on the left. If the next thing is true, it's the right. If the next thing is true, it's the top. Otherwise, it's the bottom. Okay? That's one way to do it. But you could also just make these less strict inequalities. Because, yeah, I guess the danger is if they're exactly the same distance from each side, these inequalities will never be satisfied. So, yeah, I would say make them less than or equal to, because then if you click exactly on a dot, right, then this distance left is going to be 0, the distance top is going to be 0, right? So yeah, just make them less than or equal to, and that should handle your edge case. All right, other questions on that? And you can also do things like if they click in a place that's ambiguous, you can refuse to simply acknowledge it, right? Somebody suggested this last week. right? So you could do something like if left plus 5 is less than right, and left plus 5 is less than top, and left plus 5 is less than bottom, right? And that's going to require that your distance here is significantly closer than your distance to the top. So if you clicked right here, it'll say, yeah, left. But if you were to click up here, it would say, you know, that's ambiguous. And it'll refuse to select one. All right, so next question. Could we also go over how to draw the box class? So that phrasing is a little confusing. So the box class is this class that contains information about one box, typically a set of booleans to say is the left, right, top, or bottom edge drawn, and maybe some other information like what's the initial in this box and so on. So you have an array of objects where each object is, you know, an instance of a box class, and you want to draw that to display your playing field, right? So you're going to do this in the paint method. So public void paint takes an argument graphics G. First thing you do in your paint method, call the superclass paint method. Okay, if you're getting any weird effects, if your letters are overwriting each other or lines are shifting slightly in position and so on and so forth, it's probably because you're not calling the superclass as paint. So call this erases the background, sets everything up where it's supposed to be, makes it look extra pretty. And then to actually draw the boxes, well, it can be a pair of nested loops. Right, so iterate over your rows. Iterate over your columns. You do not need to use paint component. You can, but don't feel like you have to. All you need is paint. A lot of stuff you'll find online will talk about paint component, and it's better to use paint component than paint and so on. But paint should work perfectly well. Same thing with graphics. You don't need to use graphics 2D. Graphics should work perfectly well. All right, so iterate over your rows, iterate your columns, and what do we want to do? Whatever your array is called, I'm just calling it board. We want to paint whatever we need to paint for that box in our board area. So my coding style is affected by the fact that I'm writing on paper instead of typing. So I'm going to make a temporary variable, box B equals board, row column. And if b dot left is true, let's draw the left edge. Okay, so where is the left edge? It goes from x0, y0 to x0, y0 plus 50. Okay, but what is x0? x0 is your column times 50. y0 is your row times 50. This is for element r comma c. So whatever row you're in, go down that many times 50, right, to get your y coordinate for the upper left. And then whatever column you're in, go across that many times 50 to get to the upper left corner, x0. So draw the left edge. So this should go from 50 times column, 50 times row, to 50 times column, 50 times row plus 1. Or, I guess the way I did it was y0 plus 50, so let's do it like this. 50 times row plus 50. So just draw a line from there to there, right? So g dot draw line, blah, 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 blah. Those 4 arguments. And then do the same thing for right, top, and bottom. And now you've got all the edges drawn where you need edges. I bet Anna's truck is beeping in response to this. All right, and then you can draw the initial, right? So if you've got an initial field in your box class, see if that indicates that somebody owns the box, and if it does, then use this drawstring method, which takes whatever the initial is, and then find the coordinates for the middle. Well, it's probably x0 plus about 25, and y0 plus about 25 gets you to the middle, so use that for the xy coordinates. Should the dot grid and the actual game lines be two separate arrays? I don't think they need to be. So the other thing you want to do when you're painting the board is you know, draw the dots. Do that first, maybe, or do it last, doesn't matter. Before you check to see if the left and right edges are filled in, right, you can just say, draw a circle at x0, y0, draw a circle at x0 plus 50, y0, and so on, to draw those dots. Maybe they'll get overwritten by lines, that's okay. Maybe you'll make them big dots, and so you'll see them regardless. You could do a separate pair of nested loops and just draw the dots, but you can actually do it each box that you get to in this pair of nested loops. All right, does that make sense? Fair enough. Yes, question mark. All right, so tomorrow I am going to do open lab during class time. So no lecture material tomorrow, but if people want to work on code, screen share, and so on and so forth, we will have class time tomorrow to do that. If you don't have any questions regarding PA4 or anything that you want to talk about, you're free not to come to class tomorrow. So it's just going to be open lab. And I want to do that so that people aren't scurrying Thursday, the day before this is due, to try to get help from me, right? So tomorrow, office hours at 11, office hours at 3, open lab time during class. So you can plan on finding help from me during those times if you want. All right, ready to move on to something new? So let's talk about networking. So this is our next topic for this course. And we've got less than 3 weeks left in this course, which is just amazing. Which means many of you have less than 3 weeks left at Clark, which is like totally awesome. So I want to talk about networking this week, okay? And we'll talk about it today, we'll talk about it Thursday, Friday, we'll talk about PA5. But I want to talk a little bit about networking in general terms, and how the internet, right, which is really what all of our networks, even our local and home networks, are basically structured like. I want to talk about how that is basically set up and work our way down to the code level so that we can actually write Java code to interact with things across the network. Okay, and that's going to tie into PA5. And then probably next week we'll start talking about multi-threading and being able to do what we did with forks in 224, but in a much more straightforward way. So basically creating multiple processes running inside our Java code. And that's going to tie into networking as well. And that'll be the bulk of next week. And then we're down to our last week, which will probably be SLP presentations. I still need to figure out how we're going to do that, and tying together some loose ends and so on. So we're coming rapidly to the end of all of this. which is always kind of sad, but should be like very exciting too. So let's talk about networking. And you know, computers have been around for a long time, and computers were typically these very large room-sized behemoths that you know, you had to be someone special to get access to these things. You could look at them. They usually had glass in front that you could press your nose against and stare through. But not just anybody could go and use a computer, right? So when I was in high school, I was not allowed to use the school's computer because it was one machine that was shared by a good part of New York State, and you had to be a junior or a senior and taking the one computer science class to be able to do this. So we had to sneak in and use this when nobody was looking, and then we'd get kicked out eventually, right? So computers were traditionally, you know, these relatively scarce commodities, very expensive, perceived as very fragile. And the idea of having a computer in your home or in your office or in your lab was ridiculous, right? Nobody imagined that. Computers were in the computing facility building, you know, surrounded by air conditioners and technicians and so on. But people who did want to use these things needed a way to access the computers without having to physically, you know, go into the space where the machine was. Someone walking down the street with some signs about "let classes begin." So I think they're protesting to bring school back into session. So early version of networking was basically using a terminal. And here is the main computer. It's a lot more than just a CPU, but I'll just call it CPU. And there would be these different terminals around. And they would communicate with the CPU. Again, now even this was pretty advanced because when I started in college, we didn't have terminals. We had one key punch, and you'd type your program up on physical cardboard cards and put it into the one key punch, and it would send it into the CPU, and CPU would process it. But terminals were, you know, kind of the working model through later 70s through the 80s. And what was a terminal? This was the most popular terminal. This was called a VT100. This is basically a hardware version of PuTTY. Okay. What is PuTTY? It's a program you run. It lets you type keystrokes and it sends them to the Linux server. And when the Linux server sends information back to you, PuTTY displays it on your screen. Well, that's what this device did. Okay, it was a physical implementation of PuTTY, but nowhere near as sophisticated as PuTTY, right? PuTTY will do encryption and all kinds of other things. This was for its time a really smart terminal, but relatively speaking, pretty dumb terminal. Just sends out ASCII codes, gets back ASCII codes. No color, right? It's just, you know, black and white. No ability to change fonts or font size or anything like that. You could boldface, and I think you could do inverse video to highlight. Okay, so this was, you know, the extent of networking. Basically, you would use this to communicate with the remote machine. But here's something really cool about this, right? If you had this in your laboratory, there was a wire coming out of this machine that would go, you know, disappear into the wall and somehow come out another wall in the machine room and connect to the computer. Okay, and that's great, you know. But if you had this in your office, right, which might move from location to location, you did not have a direct physical wire going from this machine to the computer. What you had was a wire going from this machine to your telephone. And you would pick up your telephone, you would dial a phone number and press a button on your phone, and this terminal would send signals to a device on your phone that would translate those into tones. And those tones would go through the telephone, and at the other end of the telephone was another machine next to the computer. And it would pick up those tones, change them into electrical signals, send those on a wire into the computer. Here's the cool thing. Same terminal, same computer, different way of transmitting the information. right? A direct line, physically connected, just sending electrical signals, or electrical signals being changed into sound tones, transmitted through the copper in the phone system, and then transmitted back into electrical signals on the other side. Okay? Made no difference to the VT100, to the terminal, made no difference to the computer. And so this is the start of what we can think of as abstraction. Okay? And this is along the same lines as modularization, right? A word that I use way too much. I've been using this word since September. Modularization is just a fancy word for saying, you know, if you want to do X, Y, Z, don't write code to do X, Y, Z right here. Make a function called do X, Y, Z and call it. Okay? It's taking a bunch of operations and putting them into a separate thing, a function, and then just calling that. Well, we do the same thing in networking. Okay, so in networking, you can find all kinds of pictures for this online, but we think of these layers of abstraction. And down here at the very bottom, this is the physical layer. This is, are we sending electrical signals across copper wires? Are we sending sound tones through a phone system? Are we sending modulated 2.4 gigahertz waves through the air? Are we sending infrared transmissions from a remote control, right? This is the lowest level of the networking. This is how the energy / matter is being manipulated to convey information, typically ones and zeros, okay? Way up here, you know, we've got things like, you know, our web browser, or our mail program, or our Minecraft server. You know, the important high-level stuff. And here's the thing, we don't want to have to download a different browser because somebody changed this lowest level from being wire to being wireless. Right? So these levels up here know nothing about the physical layer. They don't care about it. Okay? The only thing that knows about the physical layer is this data link layer. And the data link layer is basically managing sending ones and zeros, right? So if this physical layer is an old school terminal system, what do? You have a system of positive 12 volts and negative 12 volts, and you can change the voltage level on a wire. And maybe this starts off low, and the first time it goes high, you start an imaginary clock, right? And at certain intervals of that clock, you check to see if the voltage is low or high, and you interpret that as a 1 or a 0. Okay? That's a really old system called RS-232. It's still in use. Okay? You can still find things that change USB into RS-232. It's not plus or minus 12 volts usually, it's 0 and 5 now, but that's one way to transmit information, right? But it's just, you know, voltage levels. So there's another layer on top of this that basically understands, okay, when my clock goes high for the first time, when my signal goes high for the first time, start this imaginary clock. And at each tick of my imaginary clock, let's read the voltage. And let's do that 8 times, and let's put those together from least significant bit to most significant bit, and let's make a byte. And when we're done, let's make sure that the output goes low again. And if it doesn't, something went wrong. Okay? And so that's the layer that's determining how do I use this physical manipulation of matter and energy to convey ones and zeros, binary information. Okay, you might use a system where you have a pair of signals. You have a clock and you have a data line. Right? This is SPI or I2C. You find these on Arduinos and Raspberry Pis and things like that. It's a protocol based on sending a clock and a data line. And each time the clock ticks, the data line is sampled, and that's how you convey your ones and zeros. But again, none of the stuff up here cares about what's happening at these lower levels. The only thing that cares about the physical layer is the data link layer. And the only thing that cares about the data link layer is this next layer above it. So this is an abstraction, right? This is a modularization in some way. This is taking these questions of, you know, what is the byte of information that is being sent and how do I send that? And the code for these things never has to worry about that. The code up here is just going to say send a byte, give me a byte, give me 10 bytes, send 25 bytes, right? And this other set of layers manages making that happen. So we mostly talk about two layers of this. And the first layer is called IP, that's the internet layer. And the internet layer sits on top of that data link layer, okay? And it's basically responsible for sending information from one machine to another. So part of what you can do with this internet protocol IP is you can say, here's a bunch of data, right? Coming from this machine, send it to that machine. Okay, and that's the main purpose of the IP layer. Now, it's not reliable. There's no guarantee that if I send a bunch of information from machine X to machine Y, that it's going to get there. Okay, there's nothing in this layer that automatically checks to see, did it get there? No, please send it again, and so on and so forth. There's no guarantee if I send 3 messages in a row that they're going to get to the destination in the same order. So if I'm sending a message using voice over IP, right, and I break that into 3 chunks, it might show up on the receiving machine backwards. And if I just turn that into audio, someone's going to think I'm speaking in some weird language, right? So that's not the concern of this layer. This is just, here's a machine, here's another machine, here's a bunch of data. I want to transfer this data from this machine to that machine. Okay, that's what the IP layer does. And this has been around since the 70s, okay? This was developed in the 70s, and it's effectively unchanged in all that time, okay? It works. Here's a secret about technology, right? Well done technology does not need to be changed every year, okay? They won't tell you this in school often, but, you know, there's no inherent reason why things need to change and be updated every year, right? Most of the updates that you get are one of two things. They're bug fixes, right, which are called security enhancements, but they're really bug fixes. Or it's marketing, right? It's let's put some new features in here so that the version that you just bought is obsolete and you have to buy a new version. So it's a marketing thing. So this is an example of you know, something that was made to work in the 70s and it still works today, you know, 50 years later. And so you can go back and you can find documentation on this. So there's things called RFCs, requests for comments, that the government would put out when something was being developed, and it was basically a call to the public to help them figure out how to do something. So this was the Internet Protocol. This was developed by DARPA, so that's Defense Advanced Research Projects, September 1981. Okay, so this was trying to pin down this Internet Protocol. And this is a document you can still go to if you really want to work with this protocol at a low level. This tells you everything you need to know about it. Okay? And it's relatively short, especially as government documents go. And it's all just plain text, right? There's no graphics or anything in here. So, you know, detail of what the Internet Protocol is about, and so on and so forth. A view of where it sits in this hierarchy, right? So below here are the data link layer and the physical layer. Up here are the application layers, so file transfer protocol and so on and so forth. But let's come down to the good ASCII art. So there's what an internet packet looks like. Okay, this is the header of it, and it's written out, you know, 32 bits per line, just for convenience. And so, you know, there's 4 bits for version information, there's 4 bits that tell you how big the header is, and so on and so forth. But down here, these 32 bits, that's the source address. These 32 bits, that's the destination address. Okay. So what are these addresses? These addresses are, you know, these kinds of things. Right, so you see these things when you deal with the internet. It's usually 4 integer numbers separated by periods. Each of these is from 0 to 255. Well, that's 8 bits each. So this is 32 bits. All right, that's the address of a machine on the internet. Guess what? We ran out of addresses, right? At the time when this was being developed, 32 bits, that's 4 billion different numbers. Who could have imagined we'd need 4 billion distinct internet addresses, right? That would mean, you know, 4 billion computers. That's impossible, you know. That's like, you know, more than one computer per person. I heard a talk from Vint Cerf, who did a lot of this work in the 70s, and he was like, yeah, that's my bad. He claimed that there was a lot of debate about whether they should do 32 or 48 or 64 bits, and his argument was, let's just do 32 for now, and if this actually works, we can expand it later, right? And so, you know, later, as in decades, we ran out of address space and we moved to IPv6, where we have much longer address spaces. So anyway, this 32-bit source address, that's the IP address of the machine that's sending this information, and this is the 32-bit address of the machine that's receiving the information. Okay. Quick sidebar. If I look at my internet information, right, my address is 192.168.0.20. Well, that's not my address on the World Wide Web, right? That's my address in my local little home network. Okay, and my phone is 192.168.0.17 and so on. But that's a little local intranet that I have. But I'm actually connected to the internet, right, through Comcast. And if you do, you know, something like find my IP address, you know, there's my actual IPv6, there's my actual IPv4 address. And that's the unique 32-bit description of the machine that is my router, right? And anything on the net, anywhere on the planet, anywhere on the space station, can put that 32-bit representation, right? Turn each of those into 8 bits. Put that into here as a destination address, and you can send information to my machines, to my router. And my router will send them to, you know, 192.168.0.20 or whatever. Right? So this is the level that's connecting machines together, okay? But doing it unreliably without any guarantee of successful transmission and so on and so forth. And then this gets followed by data. Okay? Now what kind of data do you send? Well, we send data in a different form called TCP. That's the Transmission Control Protocol. And that's the one that handles reliability, putting things in the right order, and also saying whose data is this? Right? I'm sending information from this machine to that machine, but what is it on this machine that's sending it, and to what on the destination machine should it be sent to? So TCP is a whole nother protocol. Right, so Transmission Control Protocol. And same thing, sits on top of IP, sits underneath the higher level layers. And come down to the actual specification. So here's what a TCP header looks like. And it starts with this thing called a source port and a destination port. And these are key. We're going to come back to these shortly. Sequence numbers to put things in order, acknowledgement numbers to acknowledge receipt of a particular packet, and you know, checksum. The other IP header had a checksum too. So checksums let you know if any of the bits got flipped during transmission. So you add up, you know, 256 bytes, and you take it modulo something, and that gives you a number that if any of your data changes, probably your checksum will be different. And then this is followed by data, which is the stuff that you actually want to send from this source port to this destination port. Okay, so what's our picture here? You've got your physical layer, your data link layer, your IP layer, your internet layer, your transport layer. So this is IP, this is TCP, this is, your mail program, for example. And when you want to send a piece of mail, you create a TCP packet, and you put that inside an IP packet, and you turn that into ones and zeros, and you pump that through the physical layer. And when something comes in on the physical layer, it comes up to the data link layer, you get ones and zeros. That's interpreted as an IP packet, and from that you extract the TCP packet, and from that you figure out, oh, this is going to port 25, that's the mail program, and you send those ones and zeros to the mail program, and it does whatever it wants to do with that. This is a powerful concept. It's a model you can use in your own work, right? This idea of abstraction. We'll start to do this more in PA5, but you're already seeing it somewhat in PA4, where your mouse click does certain things. Your mouse click doesn't paint, though. Your mouse click sets things up for the paint system to handle when paint gets called, sometimes because you called repaint, right? So this is a powerful way to organize processing. All right, so I closed that too soon. So let's talk about ports. 16 bits for a source port, 16 bits for a destination port. That's 65,000 ports. So what is a port? A port is a particular, think of it as just a bucket with a 16-bit identifier associated with it. So I can have bucket 25, and I can say, hey, take these bits, put them in bucket 25. Or give me stuff from bucket 25. Let me see what's in there, right? And the destination port is, a bucket sitting on the destination machine. The source port's a bucket sitting on the source machine. And when the source machine wants to send something to the destination, right, it puts something into its source port, and the magic of the internet connects that to the destination port. Okay, so we're going to figure out that magic that makes this connection happen. All right, so these ports are called, they're just called ports, but they're going to bring us to talk about sockets. But let's look at ports. So if you're on a Linux machine, there's a file under /etc called services. And if you look in that file, you'll find a bunch of port numbers listed. Okay, now most of these don't do anything anymore. Most machines are locked down, their ports are not accessible. But it used to be that port 7 was an echo. Right, so it's using TCP, Transmission Control Protocol. If I made a TCP connection to destination port 7, I could send, hello there, and it would send back hello there. Okay, it was an echo test. And if you wanted to know if a particular machine's networking was functioning correctly, you could connect to port 7, send out a message, look for a return to it. If you wanted to know what was going on with the system status, you could talk to port 11. And it would send you information about what was going on in the system, kind of like when you say top from the command line. If you want to know what the time was, you could talk to port 13, and it would tell you its notion of what time it is. Port 21, File Transmission Protocol. This was how we would transfer files from one machine to another. You make a connection to port 21, and then by using a simple language, you could say, hey, log me in as this person, here's my password, go into this directory, send me these 3 files, right? And if you had the right program running on your end, which was also called FTP, right, it would take the stuff coming from the remote machine and use that to create copies of the files that you asked for. Okay, this stuff still works, but we don't really do this anymore. This was all terribly insecure. Okay, to log in over an internet connection is a really, really dangerous thing to do because we don't know where these network packets are traveling. The reason we have an IP layer is because I say I want to send some data from machine X to machine Y. Well, I probably don't have a direct line going from machine X to machine Y. But, you know, I have a line to a machine at Comcast down the street, and they have a line to a tower somewhere, and that goes to a satellite, and that goes somewhere else. And there's really no telling where your data is traveling from destination, from source to destination. And if part of the data in my TCP packet is a password, right, anybody can pick up that packet and see my password. Okay, I've done this accidentally when I was working with some of this stuff a long time ago, early 80s. I was playing around with it and I stumbled across one of my coworkers' passwords this way. I had to tell her to change her password. But this stuff still works, right? It's just that we shut it down in favor of more secure things, like secure logins. 23, Telnet. We'll use Telnet for what we're going to do in this course. That's like PuTTY. Lets you type and send things, lets things come back in, and you can see them. But again, insecure. 25 is the mail program. So SMTP is Simple Mail Transfer or Transport Protocol. It's a simple way to send mail. And if you have an SMTP server running on a machine, you can just connect to port 25, right? Make a TCP packet and say destination port 25. Put the machine's address in the IP header. And you can send messages to the mailer and say, hey, I'd like you to send a piece of mail. Here's who it's from, here's who it's going to, here's the subject, here's the body. And there's all kinds of other ports out there, right? And these are not hardwired in the system, these are just protocol, right? This was agreed upon, and if you went to any machine and you tried to talk to port 70, you got to something called Gopher. Okay, this is an early version of a web browser. Here's an interesting one, HTTP, port 80. That's where your web browser goes, right? And there's software running on a machine that's listening for data coming into port 80, and when it receives data, it interprets it, and if the data looks like something it understands, it sends information back. And so all the stuff we do on computers, web browsing and sending mail and logging in remotely and all that, is all just making, sending, and receiving TCP packets on top of IP packets. Right? That's what's driving all of this stuff. Minecraft, if you run a Minecraft server, right? I don't think they list that in here. It's port 25,000 something. But if you have a Minecraft server, same thing. When you're running your client, you're basically making TCP/IP packets containing, you know, whatever the user is doing, and you're sending those out through the internet, and there's something listening, your server, on the destination machine, picking those things up. There you go, 25565. Thanks, Travis. And it's all just TCP/IP. So, there's a really useful program called Telnet. And if you have a Linux system, you can just download this sudo apt install telnet or sudo apt get telnet. And you'll see people who will pass out, you know, from anxiety if they see you using telnet because it's so insecure, right? But, you know, you don't use telnet to send your password to machines, right? But telnet is a perfectly fine tool for just sending information using TCP/IP. Okay, and this program has been around forever. It works great. So here's what I can do. I can say telnet linuxenjrcs.com, and this would try to log me in for an interactive session. Well, that's not going to work. Okay, so here's the IP address of the Linux server. Okay, so that's the actual address out on the worldwide internet. And it'll try for about 30 seconds and eventually it'll give up because there is no service listening for a telnet connection. If I were to try to connect to port 22, That's the SSH login. That's what PuTTY logs into, right? And when you run PuTTY on the top of the setup options, if you click SSH, you'll see something that says port 22. That's what this is referring to. Okay. Now I don't know the magic stuff to type to do a login through this, so it's going to say, I don't know you, goodbye. Right. If I connect to port 80, I'm talking to the web server, and I can say get index.html, and it sends me the web page that you see when you connect to linux.engrcs.com, which is the Clark ECS web page, right? So it's HTML, right, with a lot of CSS and stuff. But this is, you know, the Clark web page. This is what you see when you go to this site, right? And the last thing you see here is disclaimer, the information presented here is deemed to be accurate, etc., right? Well, that's that stuff right down here. Disclaimer, this information is presented, deemed to be accurate, etc., right? So this is all TCP/IP. All right, so we really want to learn how to work with this level of networking, and Java makes it really easy. Okay, Java is going to let us very easily connect from one port to another. And so we can write a web browser in Java, we can write a mail program in Java, or we can write our own stuff in Java. We can make a networked version of the Dots game, for example, in Java. All right, so Open Lab tomorrow, and then Thursday we will start looking at how this stuff works in Java, how we actually create these connections and how this is set up, and this will be built on the idea of sockets. So we'll be talking about sockets on Thursday. All right, thanks. Have a good one.